Thanks, everybody. It is fantastic to be here. I'm really excited to talk about design for AI and AI for design, and hopefully by the end of the talk, you'll actually understand what we mean by that. To set the stage here, you have to understand what our company Cadence does. Cadence is, many people haven't necessarily heard of it, but we've actually been around as a publicly traded company for 37 years. The core mission of what we've been doing over that time is developing electronic design automation software that basically every chip that you can buy today, from a cell phone to a TV to a car, to a computer, is using Cadence software to design it. What we've done over the last 5 to 10 years is now elevated that into the system space. So now it's not just about software for building chips, but software for building systems, and then even further into molecular science. Because the core of what Cadence does is optimization and simulation. It's solving complex problems, combining math and computer science to simulate and optimize some of the most complex problems in the world. So the problems are in complexity in the multiphysics are not just in silicon anymore, but they're at the systems level and even at the molecular level. So there's a strong synergy that we are the software to solve some of the most complex problems in the world. Now, as part of this, so to see where I'm going here, we obviously have a power crunch, right? We are going from megawatts to gigawatts. And, Dr. Brown got it wrong. It's not a gigawatt, it's a gigawatt. So next time you're watching Back to the Future with your kids, you can kind of correct them about this. The trend is clear, though, because even though model sizes are not exploding anymore, they seem to have stabilized. The compute power, especially as models start to address things like physical AI and drug discovery, and you have video to train model, the computing power is going to grow very quickly. It's already growing at 2x per year and shows no signs of slowing down. And so even the data centers that are being built today, won't be on handling capacity. So we have to pay attention to all aspects of power in data center construction. And the amount of money spent on data centers is over $300 billion just by the top 4 hyperscaler companies. And overall, we see like trillions of dollars being spent. $5 trillion is just, a relatively median estimate. It could be as high as $8 trillion. So this kind of expense is enormous, but that means there's also lots of opportunity for people to build businesses and profit from this enormous expenditure. So what are the trends we see as we try and scale out, as we build data centers? Well, first of all, the energy, right? 1.5 to 3x power increase per generation. How do we kind of contain this? Well, we develop software, right, that our chip designers come to use, and we have lots and lots of low power design flows in digital, in PCB, and analog across the spectrum. Another thing is the data flow is increasing. And fortunately, there have been very interesting advances in packaging to allow 3D ICs to become a reality. We've been talking about 3D ICs for 20 years, but now they're finally here. But because of that, the problems of how do we actually build a 3D IC, how do we simulate, and there's new challenges for that. So we have a product called Integrity that is used for this thing and modeling photonics as well. Now, what about cooling, right? It used to be that, liquid cooling is going to become inevitable, right, is in order to handle this. So how do we simulate and model this? We have, simulation CFD software for this. Again, this is similar. It's all about optimization and simulation, multi-physics capability. This is our bread and butter as Cadence. And then, the refresh is going to continue to be much more accelerated. So you're going to need software. We have digital twin software that's unique in order to model data centers. So I was mentioning at its core, Cadence, principled simulation optimization. This is what we've been doing for generations. But how do we take that up a notch? Well, there's really 2 ways we're doing that. One is we're taking these core engines and we're developing hardware and we're making sure they can be accelerated on special custom hardware so that in taking days, it can take hours, or instead of taking hours, it can take minutes to do a simulation. And then the other place we're investing, so that's kind of about accelerating. The other place we're investing is in agentic AI, right? How do we take these and bring our designers, our customers up to a higher level of abstraction than we have today? And so our products have always been used to design AI chips. You probably cannot find an AI chip that's ever been built without Cadence software. But now, because we're adding AI into our systems, right, we see the reverse trend. We see a virtuous cycle. We are building the infrastructure that is helping us, build more productivity. Now, the idea that AI chips, are sort of, we're using AI to build chips. This isn't just some pipe dream. We're already at an inflection point where about half the chips built today use AI technology, right? Because we've been working on this for over 10 years. But this is going to accelerate tremendously. Even in the next 3 years, we're about 90% of chips we picture will be using AI. So this is incredibly important because, again, we see the potential of huge designer productivity improvements, which are absolutely necessary because designs are coming more complex. The cycle of design and system building we want to shorten. So the need to make designers more productive has never been higher. All right, so let's talk about agentic AI. And I like using a self-driving car analogy. I am not the only one to invent this. I'm sure you've heard this many times, but it really helps frame the discussion, right? We think about the levels of AI. So as I said, we've been working on AI for a while, what we call optimization AI, and I'll talk a little bit more about that. But then you start to really, how do we harness the power of LLMs? Well, the obvious way is conversational LLMs, right? Is that we, making sure you can ask questions, talk to our products. But then once we have that, you go to complex reasoning. And that's where you start to actually really bring up the designer to a higher level of productivity. And so, but again, the designers at level 3 are still interacting with the products. At level 4, now you're talking about agentic workflows where you can now build new tools and build agents that you've never done before. So, and by the way, you're not done with one level. We're working on all the levels at the same time including full autonomy. And what we see here is our product portfolio starts to merge because, you can imagine in the future, instead of how, we actually have hundreds of products that do different things, but imagine you're designing silicon, you could have one silicon agent that you can use and connects all the products, they become services to the silicon agent, or you're designing a system, we can have a system agent. So that's really where we see a blending of design flows happening. And underlying all of this, we have our own AI platform, which I'll talk about. Now, one way to think about this is we have self-driving cars today, right? You can go to San Francisco and you can catch a Waymo, or you can come to Austin where I'm from and they're there too. But obviously, that is not, pervasive by any means, and we're a long way away from that. So it's more like the tip of the iceberg. Now the iceberg's going to kind of grow and you'll get more of that. But meanwhile, as we go through the self-driving car journey, you cannot buy a car without lane assist. These are kind of level 2, right? If you start to veer off into your lane, you'll get this shaking, or you know what I'm talking about, or you start to back up the car and it'll beep you if you're about to hit something, which is great because I can only think about how many times I would have hit something if I didn't have that feature. So the idea is that it's kind of like a pyramid, same in design. We're deploying agentic AI everywhere. Optimization AI is pervasive. Conversational LLM is about to be pervasive. And then as you go up the pyramid and do more and more complex stuff, you attack parts of the design flow, but then gradually expand it. So I'll give examples of these. Okay, so what do I mean by optimization AI? We have many products in the marketplace already that can really improve designer productivity. Our flagship product called Cerebrus. So you're doing a physical design, and you can actually use reinforcement learning in order to get much better results. And because of that, even though there's more compute power, customers have adopted this widely. We have over 1,000 tape outs. We're probably going to stop counting now because it's been so successful. We have custom design solutions in our verification space. We can do iterations where you run a regression, and verifications are an incredibly complex problem. So you can actually use reinforcement learning to say, hey, I can actually get the same coverage without this many vectors, maybe shave it down 10% the next time, and then shave it down another 10% the next time until eventually you actually can get like 20x regression efficiency. Each time you learn a little bit more what can be removed for the next time while still getting, the same kind of coverage. So we have lots of solutions in this space, including multiphysics. This is established, but we're not done with optimization AI, and still it's a huge investment because we see the potential here. But now how do we put this into more agentic workflows? So conversational LM, right? This is really about just chatting with the documents, chatting with our online portal. And how do we enable that is by providing common infrastructure where we can put this in all our products, right? And we connect it with our own AI infrastructure called JEDI. We can connect it with our customer AI platform. We don't want to be naive and say, oh, we're the only game in town, and then have capabilities to use whatever models, whether it's on-prem or hosted. Now, we're deploying this everywhere. We're building this infrastructure and all the tools. Then the next challenge I see in the immediate future is really about how do we successfully bring up the level of abstraction for designers, right? Designers today, some tools use Pythons. They have to write RTL, Verilog. They have Skill Code, which is a language for analog design, and most products use Tcl. So customers, electrical engineers need to learn these languages to talk to tools. But imagine they didn't. Imagine they could just talk to the tools with natural language. We have coding assistants today, but coding assistants are not very good for these low propensity languages. Python's not a low propensity language. So how do we harness them? How do we train them and use RAGs in order to solve these problems for our customers? It's a very exciting, opportunity to really improve their productivity. And we're working heavily on this. Now, what do I mean by agentic workflows? So you have to pivot. When we talk about complex reasoning, coding's an example. Here's an example of a complex workflow that we're deploying. Today, when you do verification, right, you start with a specification of a document. The specification tells you, everything you need to know, about the document, and then you have to create a verification plan. This is a manual exercise. You have to create all the different collateral to say, all right, this part of the specification has this section, this has this, and creating a verification plan has to be done manually today. But this is the kind of task an LLM can be really good at. So we built agentic workflows to go from specification to a verification plan. And even analyzing the spec, understanding the spec, removing ambiguity, right, is a task. And we need to keep designers in the loop a bit. If you try and automate everything and say we're done for you, you're going to lose some information, right? If you lose a little bit of information from one level to the next, that's going to be terrible. So you have to keep designers in the loop, build agentic workflows, but build that feedback mechanism, especially to remove ambiguity. So you build a verification plan, but that's not enough. Now you can take the verification plan and build the collateral needed to actually understand what's going on. This is what I mean by test bench, system Verilog assertions. You need all this collateral in order to actually run a simulation or run formal methods to verify, is my design correct? But where's my design? Right? Well, that's where this RTL generation agent comes in. You actually can start with a specification and generate RTL. And this is kind of what I was talking about a little bit about language generation. This is a very exciting time. RTL and writing RTL is a very cumbersome process. It's a process that designers have to have expertise in. And so doing this correctly is still a huge challenge for their industry. LLMs are getting better at that, but how do we harness them and guide them to do things correctly? Also, incrementality is really important, right? It's very rare to start with a design with no verification collateral, with no spec. It's always, I've got version N, now I need version N+1, and what is the incremental stuff you have? Okay. So we've only gotten halfway through the slide, but the idea is now you have the collateral to run our core simulation tools. You can run our simulation, you can run Palladium, and then you can actually iterate on your design and say, wait, this regression failed. Why did it fail? Well, we want to have automatic debug and analyze and optimization that goes back and changes the collateral. It could change the test bench, or maybe it could change the RTL. And that's what we mean by a truly agentic workflow. This is what I mean by level 4. Now, if you talk about level 5, this is like truly autonomous, right? Push a button and get your chip, having this silicon agent where you're really connecting many, many different agents. When I talk about collateral generation, you're going to need a test bench agent, a schematic agent, floor plan, all these things that are, designing a chip is one of the most complex things humans have ever done. And the amount of collateral design teams have to generate is enormous. Aiding in this process, right? Building this is like bottom up, but then you have workflows and connections. But we're also not naive enough to think that customers aren't going to do it too. We need to build connections and use common protocols like MCP and A2A to connect with agents that our customers can build, right? This is very, very important, So this is really where we're going with this. And just like, self-driving cars are here. They're here, but they're not here. I see this being something that evolves over time. We will get there, but then will it be, limited and gradually grow in capacity, grow in scope, where it becomes more useful to the masses. Now, I talked about the trends. Okay, so, now to pivot away from building AI agents to how do we use the infrastructure. So 3D IC, I talked a little bit about before how, interconnect, right? That data flow throughput is incredibly important. And 3D IC is a revolutionary technology that allows us to stack chips in a way we never could have before. But this brings all kinds of new design challenges. And you need software to understand what's going on. So we have a platform called Integrity 3D IC, and you can see sort of in the lower left here, you can say, just take 2 dies, and you want to simulate this. This is a massive system-level simulation that's very difficult, and obviously you can then find, oh, look, we have a hotspot in one of the corners that's going to make it, not viable, that this has to be fixed. And so this is a key technology that we provide. But you can imagine the complexity of simulating an entire stack, and having the multi-physics to do it is actually incredibly time consuming and resource intensive. So that's why we've invested heavily in optimizing, in making our systems work on GPUs, right? Using NVIDIA platform GPUs, we can accelerate this kind of simulation. And the great news is as these systems get better and better and we add more GPUs, we get more acceleration, right? We doubling the number of GPUs doubles the time, cuts the time in half. Sorry. You can double the capacity. And so we see things like 19x speed ups in static thermal simulation, or 12x speedups in transient thermal simulations today, 8x speedups in warpage simulation. So these kind of accelerations are incredibly powerful for these kind of problems and are incredibly important as we build the next generation of AI infrastructure. Another piece of hardware that we announced last year, we've been building this for a long time. This is the 3rd generation of Palladium. And actually, Jensen Huang from NVIDIA said this is his favorite appliance next to his refrigerator. So you can see the value. And why would he say something like that? Well, because NVIDIA designed some of the most complex, things in the world. The latest Blackwell was one of the biggest designs ever, and it could fit in a Palladium. They could simulate the power of the entire thing. Otherwise, they wouldn't have cycle-accurate power analysis. We also have hardware, Millennium, that is used to not just for simulating chips, but can solve multiple problems, right? Built on top of, again, NVIDIA architectures and their GPUs, we can take some of the common problems, accelerate them in silicon design. So these are just examples, like IR drop can go from days to hours. And in system design, transient simulation, as I said, can go from hours to minutes. Using this kind of, you get this virtuous cycle of code design where the software is designed for this hardware, and then the hardware is designed to handle these kind of software problems. So you get this virtuous cycle of goodness. Now, we talked directly about data centers. One of our key pieces of software is called Reality, where you actually get a digital twin of the data center. This is a unique offering. I think only Cadence has something that can actually simulate what a data center is, not only as you are building it, but also once you have built it. You constantly change it. There's constantly ECO, so you need to monitor. Having a live simulation of all the different aspects of the data center is paramount. It allows you, and then because you can simulate, you can see where the problems are. So you can increase capacity, you can reduce energy, because you actually know what's going on with cycle accurate simulation. Now, to make this effective, you have to have models, right? And so we have this whole ecosystem, digital twin ecosystem, where we have over 14,000 models of the data center and 750 vendors that supply it. There's a standard OpenUSD that we use, and so it's very easy to contribute to this ecosystem. And just recently announced now the latest NVIDIA Grace Blackwell SuperPod, right? This now has a model, and so if you're building data centers with this, which many people will be, of course, you can now use RealityDC. And if you are not using this, if you're building components of a data center but don't have a model, please contact us. Let's get you into our ecosystem. So if we look at where this is going, right? This is what we see. We're all invested right now. This is AI, something in the infrastructure AI, and this is where companies are investing. And what we're really trying to show here is that the silicon and system volume and compute is only going to keep increasing dramatically as we do principles, as we use our core infrastructure. We see a trend where, soon it really will be all about physical AI, where we're talking about self-driving cars, drones, and especially robotics. As robotics work their way more into the mainstream, we all have seen, the keynotes with the cute dogs running around, but this is going to become real soon and have real value over the next, say, 2 to 7 years. And to train models to handle this kind of, physical AI, again, the compute's going to just continue to explode. And then, once we get there, then what about life sciences, right? What about drug discovery? This is the untapped potential of AI. We can see that this will become really a huge, huge opportunity for the space. I mean, if we think physical AI is big, I think that, the life sciences and trying to actually improve healthcare and use AI to solve the kind of problems that are just unimaginably complex today could actually become a reality. So, in summary, if you think about what we do, right? Cadence at its foundation and its history has always been about designer productivity, developing software and electronic design automation, and we've expanded that to system design and also life sciences. This is the middle part of what we call our 3-layer cake. Now we take all this core software, this core expertise in math and CS, and we accelerate it, right? We build custom hardware like Millennium and Palladium, and we can now, accelerate the foundation so that customers can be way more productive with using our software. But then it's not just about making our software better. We need to bring the designers up to a higher level of abstractions. I talk about adding AI agents, adding agentic AI capabilities across our software portfolio will really be a game changer for designer productivity. And so, so hopefully by now you see how we do designing for AI, which we've been doing every AI chip, and now how we have AI for design. Thank you.